Ladies and gentlemen, welcome to the webinar this evening, Corneal Biomechanics, Applications in Refractive Surgery. My name is David Taylor. I'm a product manager for Reichert Ophthalmic Instruments, and I've been responsible for clinical studies and product management of the Ocular Response Analyzer for about the past 7 years. We're honored and pleased to have with us tonight Dr. Stephen Stetson, of Sharpest Vision of New York, New Jersey, and Connecticut, and also Rex Hamilton, Director of the UCLA Refractive Surgery Center and an Assistant Professor of the Jules Stein Eye Institute. Later in the evening, the inventor of the Ocular Response Analyzer, David Luce, will be joining us to present some new information about waveform or measurement signal-based keratoconus risk analysis. So I'm just going to do a small introduction here about Ocular Response Analyzer. For those of you who are unfamiliar with the instrument, that's what the device looks like, and it measures 4 primary parameters. We call them corneal hysteresis, corneal resistance factor, IOP-G, and IOP-CC. We're not going to spend too much time talking about the IOP measurements tonight. They are very accurate and repeatable IOP measurements, and the IOP-CC measurement is compensated for biomechanical properties of the cornea, and there is evidence in the literature that this measurement is less affected by corneal properties than other measurements of tonometry are capable of. But tonight, because we're talking about refractive surgery, we're going to concentrate primarily on the corneal hysteresis and corneal resistance factor measurements, as these are the only in vivo measurements of corneal biomechanical properties in the world. Let's talk about a few very basic physics concepts. First, elasticity is the property of a substance that enables it to change its length or shape in direct response to a force and to recover from this deformation to its original configuration. The deformation is directly proportional to the applied force. So when you're talking about something that has elastic properties like this coil spring that's pictured here, if you apply a force to it, it will return back to its original shape when you release the force. And the amount of force required to bend it or deform it a particular amount is not related to the speed at which you deform it. Now we'll talk about viscosity a little bit. Viscosity is resistance to flow, and this is a property usually of fluids or gases. The difference between elasticity and viscosity is that viscosity's resistance applies primarily on the rate or the speed at which the force is applied. And then the term damping also gets brought into the discussion, and damping is a restraining of vibratory motion such as mechanical oscillations by dissipation of energy. I have here a picture of a shock absorber from a car. So those are 3 terms we hear when we start to talk about corneal biomechanical properties: elasticity, viscosity, and damping. And why is that? Well, the reason is because the cornea, like this strut assembly from an automobile over here, is a visco-elastic system. It contains elements of both elastic resistance and viscous resistance. And those things come into play during the measurement of the ORA process. How do we do this measurement? We shine a beam of infrared light at the cornea, and we monitor that reflected light with a photodetector. The air pulse causes the cornea to deform, and as the cornea reaches a state of applanation, similar to what a Goldman tonometer does, the maximum amount of reflected infrared light enters the photodetector. This is called P1, or inward applanation. And at this point, we record that pressure value. The cornea then enters a state of concavity, and that's what triggers the air pulse to reduce in velocity, or force being applied to the cornea. And the cornea then begins to return to its normal configuration, once again passing through an applanated state. So this is the second applanation. We refer to this process as a dynamic bidirectional applanation because it's rapid, dynamic, and bidirectional in that the cornea moves inward and then outward. And during that process we get 2 applanation pressure values, an inward and an outward applanation. And then the cornea returns to its normal configuration. The measurement signal looks like this. This is an actual measurement signal, and what you see here in green is the air pulse increasing and then decreasing in applied force to the cornea. And the red light here is a direct reflection of the light that hits the photodetector that is being reflected from the surface of the cornea. So those two peaks represent the two applanation events, one as the cornea is moving in, which we refer to as P1, pressure 1, and the other as the cornea is returning to its original configuration, which we refer to as P2. The difference between those two pressure measurements is hysteresis. What is hysteresis? Hysteresis is a property of physical systems that do not instantly follow forces applied to them but react slowly or do not return completely to their original state. This term has been around since 1890, and it was coined by this guy here, Sir James Alfred Ewing. Corneal hysteresis specifically refers to the difference in the inward and outward pressure values that are obtained during the ORA measurement process. So the term is specific to exactly what we're doing here in the ORA. Corneal resistance factor is another parameter that we will talk about tonight, and this is basically a mathematical optimization of the corneal hysteresis parameter that's based on normal population ORA measurements and central corneal thickness data. The derivation of the CRF parameter is outside of the scope of this discussion, but if anybody's interested in that, we can talk about that directly at another point in time. It's similar to corneal hysteresis, but it gives us a better overall indication of total corneal viscoelastic properties. And as such, it is a more sensitive and specific tool for use in refractive surgery decision-making. Why are these parameters, corneal hysteresis and corneal resistance factor, of interest in refractive surgery? They are repeatable in an individual eye, but they differ from person to person. They are not strongly correlated with other common measurements of the eye, except for a weak but significant correlation with central corneal thickness. They are significantly lower in keratoconus patients, and these measurements are correlated with the severity of keratoconus. And they are permanently reduced after ablative refractive surgery procedures. These parameters, hysteresis and corneal resistance factor, are indicators of corneal viscoelastic properties, which are a key to the measurement of corneal biomechanical properties. And these measurements are not obtainable in vivo by any other means of measurement. These are tissue properties, and other parameters that we're familiar with, such as thickness and topography, are geometrical aspects of the cornea. And just one slide from a peer-reviewed publication, this is from Dr. Alio in Spain, basically showing the difference here. In blue, you see a normal population. This is the distribution of those hysteresis values from approximately 8 to 15. And in yellow, you see a keratoconus population with a distribution of about 5 to 10 in this population. And then in the red lines, you see a post-lasik population. So you can see that there are statistically significantly differences between these three populations. The reason we're very interested in this in a refractive surgery population is because every eye that undergoes an ablative refractive surgery procedure experiences a reduction in corneal hysteresis. And if you see this one data point over here, preoperatively, this patient had a lower hysteresis than the average of the post-op. And this patient, in fact, has a lower hysteresis than the average of a keratoconus population, which makes this person interesting because the topography and corneal thickness in this person were normal. So we're talking about strength characteristics of the cornea that differ from geometrical aspects that we are commonly familiar with, and that's why this is of interest in our discussion tonight.